types of particles in complicated systems that are called anyons, anything in between bosons and fermions, but never mind, these are too complicated for us. So there are bosons or fermions, and they obey a different statistics that was discovered in one case by Bose and Einstein, and in the other case by Fermi and Dirac. So we'll see what are the consequences of these two different statistics, and in particular for bosons, we will describe the phenomenon of Bose condensation, which is a phenomenon that is very important in statistical mechanics, and we will probably finish describing the theory of phonons, of specific heat in solids using phonons and Bose-Einstein statistics, okay? And violations of equipartition theorem and things of this type. So this is the plan, okay? Is it clear? Yeah. No problem whatsoever. Good. So now that you're all excited about this plan, we can start with simple things. So by the way, I will ask you frequently, so it's not really necessary that you take detailed notes about what I'm saying, because the reason I'm using technology is that unlike the blackboard, I cannot take a blackboard and give it to you at the end of the lecture, but I can send you the slides that I'm writing here, okay, in PDF format. So at the end of this lecture, I will give you well, I could ask the emails to, but I will give you a piece of paper. You will write down your emails. Then I will send a collective email at the end of each lecture with the slides, okay? So it's not necessary that you take detailed notes, and it's much better that you listen to what I'm saying rather than suffering to write down each single equation. But what is important is that during the lectures, I will frequently ask you to solve a little problem, to think about something, ask you questions, etc., etc. We are going to be interactive, okay? So it's not going to be, a boring lecture in which I'm talking and you're writing all the time. I'm going to check whether you understand what I'm saying. So today I'm going to start by doing it on probabilities. So do some very simple calculations. I know that you know how to do calculations on probability, but it's just to train ourselves for this mode of operation, okay, in this class. All right, so let's start with probabilities then. All right, so, well, probability theory is, so it's very easy to describe what is a probability distribution. Essentially, if you have any system which has, or anything that has a certain set of configuration n, which are discrete, okay? For example, think about a dice or a coin. A coin has two possible configurations. A dice, if it's a simple dice with 6 faces, has 6 possible configurations. So you have this set of configuration n that belong to a certain countable set C, and then to each one of these configurations, if you can associate to each one of these configurations a number, a positive number Pn, such that sum over n of Pn sums up to 1, then you can call this a probability distribution, okay? So formally this is what it is. But what is describing this probability distribution? Well, typically, when you think about it, it describes, for example, what is the frequency of occurrence of a certain event when you repeat the same experiment many times. For example, you throw a dice many times, you ask yourself, what is the frequency with which the number 1 is coming out, and you find out easily if you perform this experiment that is 1 over 6, unless you're cheating. Okay, unless you have one of those cheating dice that can be there. If you throw a coin, for example, you have two probabilities, P of head equal to P of tails, which are equal to 1/2. All right? Now, probabilities have to satisfy a certain law of composition, right? For example, if I ask myself, what is the probability that by throwing a dice I will get 1 or 3? Okay? So I know that the probability of getting 1 is 1/6. The probability of getting 3 is 1/6. The probability of getting 1 or 3 is the sum of the two probabilities, right? So is 1/3, right? So when I have a pair of events or a sequence of events and I want to find what is the probability to get this or that, then I have to sum them. If instead I want to find what is the probability of having a pair of events occurring, for example, what is the probability that if I throw a dice twice, I will get 1 and 3? Okay, so what do I have to do? I have to multiply the probabilities. Okay, so probability of 1 and 3 is equal to the product of 1/6. The reason is very simple. If you think about it, if you have this pair of events occurring, and for example, think about the dice, they are uniformly distributed, what is the number of configurations that you will get for pairs of events? Is 36 configurations, and then this is just one of these 36 configurations. They are uniformly distributed, so you will get 1/36 probability. Okay? But this is a general statement. So if I have this or that, I sum the probabilities. This and that, I multiply the probabilities. All right, so these are the basic requirements for a probability distribution. Now, typically, when you have a probability distribution, one thing you might be interested in figuring out is what is the average of the quantity or of a certain quantity with respect to that probability distribution. For example, suppose that you have a certain quantity A, which is a function of the configurations n. Okay, A is a number, is a certain number. Okay, it's a function of n. So it's a function from n to the real numbers. And then I want to find out what is the nth moment of A. So nth moment is the average of A to the power n. The average of A to the power n in probability theory is called the nth moment of A. Okay? So this is equal to what? Is equal to the sum over n belonging to C of an to the power n times Pn. Okay? So this is the definition. So in particular, the first moment is just the average. When n is equal to 1, is just the average. Okay? When n is equal to 2, you have, well, the square. We'll see what it is. Now, for example, I don't know if you have ever done this exercise, but if you have a dice, okay, so what is the average number that you will get by throwing a dice? Let's see who is the quickest.
3.5.
Sorry, 3.5. That's correct. 3.5. You can do the calculation yourself and check it out. She's right. It's 3.5. Now, there is another quantity that is important to characterize a probability distribution, which is, for example, what are the fluctuations of a certain physical quantity. For example, so fluctuations can be defined by this formula, the average of A squared minus A squared. All right? you can just use the definitions. Now, for example, if I now throw a dice, what are the fluctuations of the number? This is a bit slightly less immediate, perhaps. But what are the fluctuations? I will do it myself in a second, but so what do we need to do in order to compute the fluctuations? So we need to compute average of A squared. Well, first of all, can we guess what are the fluctuations? How wide is this distribution? It's uniform, right? So it's going to be as wide as the average. So the guess is, if the average is 3.5, what is going to be 3.5? So the answer is 3.5. All right, so let's find this 3.5. How do we find it? Well, A squared is what? Is sum over n Pn times A squared. A is the number, so is n squared. So it's sum over n from 1 to 6, Pn, which is 1/6, n squared. Right? Now you do this calculation, well, you will get, that is 1/6, 1 plus 4 plus 9 plus etc. up to 36. Okay? Then you have to subtract A squared. Right? A squared is what? Is 3.5, which is 7 divided by 2 is 49 divided by 4, right? Now, if you take these two things and you do them carefully, hopefully not using a computer, because these are simple calculations, if I have done them correctly, you should get that this A squared minus A squared should be equal to 7 over 2, which is 3.5 again. All right? Check it. It's not difficult. Okay? Maybe I'm wrong. Who knows? I should stop recording. All right? So, and in particular, the thing, I mean, we will see later on when we'll be discussing the central limit theorem, but one thing that is important is to distinguish between the, in a probability distribution, between the standard deviation and the variance. Okay? So the standard deviation, if I'm not mistaken, is this one, and the variance is sigma A, which is the square root of this stuff. But to be honest, I always mess up between these two quantities. It's probably the other way around. I never remember, so check it. It's one or the other. The one that is important is sigma A, okay? I'm always confused about who is standard and who is variance. Anyway, so this is equal to 1.8. Now, you will see later on that this is the one that is important because actually, when we will discussing the sum of independently drawn quantities and the central limit theorem, this is going to be characterizing the Gaussian distribution that happens to be the limit of any distribution when you consider the sum of independent quantities. Okay? Anyway, I didn't write it down. Yeah, anyway. All right, so this said, these are not the only two. So, by the way, the average is also called the first cumulant. The variance is called the second cumulant. And of course, there are many other cumulants, the third, the fourth, etc., of a generic probability distribution that describe more in detail how the probability distribution looks like. For example, there is a third cumulant that has a much easier to remember name. It's called the kurtosis. And so on and so forth. Third cumulant. So you see, moments of a quantity are a to the power n. Cumulants are when you subtract to a certain power of a lower moments. For example, you consider the variation of a squared with respect to the average of a squared, and so on and so forth. This cumulant here, for example, characterizes how asymmetric your probability distribution looks like. If your probability distribution is perfectly symmetric and nice looking, as most of the probability distributions that occur in physics are, then this kurtosis is 0, and you just have the first and the second cumulant, and you have what is known as a Gaussian distribution. We will see this later on. Alright, so now, typically, you might want to calculate cumulants, by hand, one by one, or there is a trick to calculate all moments or all cumulants in one shot, which is, and this trick is essentially consists in computing what is known as a cumulant generating function. Okay? Cumulant generating function, or let's start with the moment generating function. The moment generating function is defined as the average of e to the a times t. Okay? Now, if you think about this definition, now writing it down properly, this would be now, if you think about this definition, the reason this is a cumulant generating function is that if I take, is because of a property of, it's because of a property of the exponential. If I take a derivative of the exponential, I will pull down powers of a, of the coefficient of t down here, and then I take t equal to 0, and I have those powers themselves. So in practice, what I'm saying is that the nth derivative of g of t with respect to t, evaluated at t equal to 0, is obviously equal to a to the power n average. Okay? So that is why this is called a moment generating function. Now, mind something, I'm going to say something that probably for most of you doesn't mean anything, but it's like one of those things that your grandmother said that you remember the whole life. So remember what I'm saying. This trick of computing moments by taking derivatives with respect to conjugate parameters is something that is very common in physics. You will do it, for example, when you will study quantum field theories, and you will start computing green functions by taking derivatives with respect to what is known as a source field. Okay? All of these things that look extremely fancy, because they look fancy, they sound fancy, source fields, green functions, are essentially the same stuff as probability theory in their essence. So if you understand well how it works here, you will understand very well how it works in quantum field theory. Okay, so it's important to dwell on these little details at this moment. All right. Now, in particular, what I just said implies that the moment generating function.
Sorry, is it capital G or?
Is my G. I don't know. It is a capital G.
Okay.
That sometimes I write like this, sometimes I write like this. Yeah, it's a capital G. Sorry. What does it look like?
Something like 9.
Something like 9. Yeah, it's a capital G. All right, so anyway, well, you will see, I mean, I get extremely fancy when I write an H. All right, so G of t has a series expansion, which is very simple, as you can easily imagine. It's over n from 0 to plus infinity, a to the power n times t n over n factorial. In other words, the coefficients of the series expansion of g of t are the moments of the probability distribution. Now, what about computing? So this is for the moments. Let's write it down here in red. Moment generating function. Now, what about cumulants? Now, for cumulants, it's only slightly more complicated. If I want to compute cumulants, you have to resort to what is known as a cumulant expansion. So I will do it here. You will see that we will use it throughout this course. So listen to me now, and it will be easier later on when we will do it for more complicated calculations. A cumulant expansion works as follows. If you take the logarithm of g of t, then this is equal to the log of 1 plus average of a times t plus average of a squared, t squared over 2 plus etc, etc, etc. All right? And now you expanding series of t to this log. Okay? Now you will see that the first order term is average of a times t. Now the second order term will get a contribution from this minus the square of this divided by 2, because this is the series expansion of the logarithm. And I'm collecting all terms proportional to t squared. So I will get plus average of a squared minus a squared t squared over 2 plus etc, etc, etc. Okay? So this is equal to, well, so I don't know, let's call this k1t plus k2 t squared over 2 plus etc, etc, etc. Okay? So this is the first cumulant, k1, cumulant 1. This is the second cumulant, and so on and so far. If you will go to higher orders, you will get the third cumulant, the fourth cumulant, and so on.
Are we doing Taylor expansion here?
Yeah, we're doing the Taylor expansion of the log.
In terms of t.
In terms of t, right? So if you remember, the Taylor expansion of the log is log of 1 plus x equal to x minus x squared divided by 2 plus etc, etc, plus x cubed divided by 3, right? And so on and so far, with an alternating sign. Okay? And you see that if I do this expansion here, so the first order term in t is going to be at. Then I will have a second order term, which is just, well, this one that comes from the first order expansion, a squared t squared over 2, minus this thing that is just the square of this divided by 2. Okay? And so on and so far. If I go to third order, it's going to be slightly more complicated because I will have to collect many terms. But what you can easily prove, and I'm not going to prove it, you can, I don't know whether, well, probably there is a proof of this in Wikipedia, I suspect, or in any book of probability theory. You can prove that if you introduce now a cumulant generating function, let's call it L of t equal to the log of g of t, the logarithm of the moment generating function, then this one has a series expansion in t where all the coefficients that starts with the first order, not with the zeroth order, where all the coefficients are the cumulants of the corresponding probability distribution. Okay? So if you don't know how to compute cumulants because, well, you're too messy or you don't remember them, just compute the moment generating function, take the log, expand in series or take derivatives, and you will have all the cumulants, the third order, the fourth order, without remembering all this a cubed minus 3 times a squared times a plus twice a cube, etc., etc., without remembering all these formulas. Okay? So Kn, Tn divided by
N
n.
factorial?
No, n is not n factorial, it's n. Good. Now, this said, now you will have, unless there is a genius in this class, which is possible, I'm asking you, you will have to use paper and pencil. And let's see who gets first to the cumulative generating function of the probability distribution of throwing a dice. Not putting a certain number, but sorry, the moment generating function. Moment generating function. What is the moment generating function? Moment generating function is the average of E,
For dice?
for a dice, is the average of E to the n times t, where n is the number that you get when throwing the dice. So what is the what is the corresponding moment generating function?
Is it 1 plus e to t over 2?
1 plus
E to t over 2?
Unless I've made a mistake, it's not. I could have made a mistake.
Everything multiplied by half.
Sorry?
Multiplied by half.
You finished?
Exponential big times exponential.
So let me see the formula, then it's much easier. Yeah. Yours? Yes, it's cool. Right, we have got the first. So let me briefly tell you how to do that. So this is equal to sum for n from 1 to 6, e to the t to the power n divided by 6. all right? So now, this is a geometric sum, right? You use the standard formula for geometric sums, which is, well, we have 1, 6 in front, and then the formula for geometric sums, which is, so if we call this R, is R minus R to the power n plus 1 divided by 1 minus R, correct? No. So it should be R minus R to the power n plus 1 divided by 1 minus R. Sorry, no. Yes. Correct? And then if you substitute what is R, you will get 1 over 6, and then you will get e to the 7t minus e to the t divided by e to the t minus 1. Okay? So that's it. Now you have this formula. You can take derivatives with respect to t and get all the moments. You can take the logarithm of this formula and take derivatives with respect to t at t equals 0 and get all the cumulants. Okay? You see how easy it is. It's much more compact than doing calculations. By the way, the reason it is, again, you will see objects of this type, averages of exponentials, appearing in physics everywhere in statistical mechanics. And, in hindsight, the reason is exactly this, that it's much easier to compute and to describe probability distributions in terms of cumulant generating functions or of moment generating functions than using probability distributions themselves. Okay? All right. Now, among all possible probability distributions, okay, so this was for, all I've described up to now is for discrete probability distributions. Of course, you can generalize everything to continuous probability distributions or probability densities, better said. In particular, if I have a certain variable that belongs to an interval a and b, I can define a probability density p of x in such a way to be a function, a positive function, such that the integral between a and b of dx is equal to 1. And I will interpret p of x dx as the probability of having of the event x occurring between x and x plus dx. Okay? So probability of being between x and x plus dx. All right. Among all possible probability distributions, there are two very special ones. Okay, if you start classifying them in terms of cumulants. So there's one which has only the first cumulant and nothing else, which is, let's see if someone knows what is the probability distribution that has only the first cumulant and no other cumulant. All the others are 0. Sorry?
Gaussian.
No, the Gaussian has 2 cumulants. Is a limit of a Gaussian, is a Dirac delta function. Is a Dirac delta function. So the Dirac delta function is, well, strictly speaking, is not a function, is a distribution mathematically. Forget about this. We are not going to discriminate between functions and distributions in this course. We understand what it is. And So if you compute the moment generating function, it is e to the tx is equal to eta, and the logarithm of the moment generating function is t times a, right? And you see there is only the first moment, no other moment. It's very simple, it's a linear function. Okay? If instead I want to have the first and the second moment, as your colleague was saying a moment ago, I need to introduce another special distribution that is known as a Gaussian distribution.
Sorry, can I have a question?
Yes.
The reason why Dirac delta function has only one cumulant on the first one is the reason because it has zero width.
Yeah, it's the limit of a Gaussian for width going to zero, strictly speaking. And it's not only the limit of a Gaussian, it's the limit of many other functions for width going to zero.
So generally speaking, if we have a distribution which has zero width, it must have only one cumulant. Is that a truth or not?
Well, yeah, strictly speaking, look, I don't want to enter mathematical details because having zero width and having an integral equal to 1, but strictly speaking, you're just telling me if your distribution is a Dirac delta, then it has one cumulant. So, because the Dirac delta is essentially the limit of a set of functions such that the integral is normalized to 1, and there is only one cumulant. So, strictly speaking, that's what you're saying. It's a tautology, isn't it? That's how Dirac delta is defined. Now, I don't know if mathematicians invented something more complicated than this. You have to ask them. I have no idea. Now, Gaussian distribution, P of x. So a Gaussian distribution is described by two parameters, sigma, which is the width of the distribution, and the average, mu. Now, this is normalized to 1, as you can easily convince yourself by taking an integral. I assume that all of you know how to do Gaussian integrals. Okay? If not, there is a wonderful Wikipedia page that you can easily check on your cell phone. That's what I do every time I forget the formula. So we're lucky enough that we don't have to be like Euler, who remembered everything by heart, right? We have cell phones. And now, what is the cumulant generating function? Sorry, the moment generating function. Well, we just have to compute the average, et of x. Now, this average turns out to be, not surprisingly, a Gaussian integral. To sigma squared by sigma times e t of x. Now, if you use now the formula for Gaussian integrals, certified by Wikipedia, plus c of x equal to square root of pi over b c squared over 4 times b, you will easily be able to fill out the gaps of these calculations and discover that this is equal to, you see it has the same structure. Essentially it has a linear term, it has a quadratic term, exactly as what we have here. Linear term, quadratic term, then we are going to have a linear term proportional to mu, a constant that stays in front of everything, and then another linear term. You use that formula that I've shown you before, and you will get that your g of t is equal to e to the t mu plus sigma squared t squared over 2. Actually, I could write down this formula without even doing the calculations, because if I know how to interpret properly what is mu and what is sigma, right? So mu is the average and sigma is the width of the distribution. And you see that if now I take the cumulant generating function, this is going to be T mu plus sigma squared T squared over 2. In other words, mu is the first cumulant and sigma squared is the second cumulant of this distribution, okay? And all the others are 0. The function is perfectly symmetrical, etc., etc., etc. So the peculiarity of the Gaussian distribution is that unlike the Dirac delta, it has also a second cumulant sigma that is finite. All right. Now, why the Gaussian distribution is so important in physics and in everything, actually. The reason is a theorem that is known as the central limit theorem. So let's write it down. Central limit . Have you ever seen it? The central limit theorem. First time you see it? Oh, you have seen it. Have nobody else has seen it?
I might have seen it, but
sometimes, perhaps.
no, but the name might be different.
Okay, good. So anyway, let's see if I tell you what is the central limit theorem, if you know it or not. So the central limit theorem says the following, that if I take the probability distribution of a quantity x, which is the sum for I equal to 1 to n of identically distributed variables, okay? So the probability distribution of each xi is the same, can be generalized, but let's stick to this case. Then the limit, and I computed the probability distribution of x, the limit of this probability distribution for n going to n very large, this n here very large, is a Gaussian. All right? So essentially, if I look at the probability distribution of a sum of equally distributed independent variables, then if these variables are very many, I will have essentially a Gaussian distribution. Clear? So that is why, for example, when you were taught, error propagation or things of this type, I'm sure that I remember when I did the first classes on this and when I was a student, people use only averages, width of the sigma, and tell you how to propagate errors in terms of those. Because essentially, when you look at the macroscopic world, practically, if I would want to know what is the probability distribution of, I don't know, let me think. Well, I'll give you an example, something that you can do at home, right? So maybe you can do it as an exercise. Suppose that you do the following, you ask your computer to do the following. You ask your computer to have, I don't know, 30 dice. Okay, so, and you throw each dice and you get a number between 1 and 6. And then so the number will be, let's call it Ni, where I varies between 1 and 30. And then you construct the following variable, n equal to sum over I and I. Okay? So it's the sum of independent equally distributed variables. Okay? Each dice is independent, that they are not correlated, and so on and so forth. And now you repeat this experiment of throwing 30 dice many, many times and constructing this object many, many times. I don't know, 10,000 times. And you draw the histogram of the outcomes that you obtained. Okay? And what you will see is that this histogram will look like a Gaussian. And as you increase the number n from 30 to 50, it will look much more like a Gaussian, and from 50 to 100, it will be much more like a Gaussian, and so on and so forth. In the limit of n very, very large, is going to be a perfect Gaussian. Okay? You can do it at home. I actually, last year, students did it on the computer. It's an exercise that you can do in probably 10 minutes, if you know how to write a simple code. Now, there is a reason why it looks like a Gaussian. Now, before proving for you the central limit theorem, let me try to explain the reason. So, essentially, we can guess what is going to be the average of this number n, right? So, it's going to be 30 times 3.5, okay? So, 30 times 3.5 is what? Is 90, is 105, right? Now, if you look at this number, right, it turns out that there are very many outcomes that will produce a number that is close to this one. If you want to get a number that is, I don't know, 30, there's only one outcome that will produce 30, which is 1, 1, 1, 1, 1, 1. If you want to get 6 times 30, right, there is only one outcome that will produce 6 times 30, which is 6, 6, 6, 6, 6, 30 times. But if you want to get something close to the average, there's actually exponentially many configurations that will get close to this number. And they become exponentially larger the larger is n. The larger is the number of dice you're throwing. Okay? It's as if you have a lot of configurations that give you something close to the average, and in the extreme, a very low number of configurations that will give you there. So the probability to be in the extreme, in the tails of the distribution, is essentially 0, because, well, you know it better than me. The chance that you will get 1, 1, 1, 1, 1 30 times without cheating.
1 over 6 to the power of 30.
Yeah, so it's exponentially small, right? While the chance of getting close to the average is going to be exponentially large, right? And that is exactly why in the limit of n going to infinity, all these distributions actually look like this wonderful Gaussian, intuitively, okay? So now I'm going to prove you formally why this happens, but it's important for you to understand this argument. It's actually called in physics an entropic argument, because I'm just counting configurations. And we will see that entropy is something that essentially does this, counts configurations. We will see it in the next lecture. In the next lecture, I'm going to introduce entropy from the point of view of information theory. Don't get scared, it's something very, very simple. All right, so now, how to prove the central limit theorem formally? It's actually very, very simple using moment generating functions. So the probability distribution for this variable big X is equal to the integral dx1, dx2, etc., dxn of p of x1, p of xn, delta of x minus sum over I from 1 to n xi. Okay? So this is the definition of this probability distribution. So now, suppose that now we compute the cumulant, the moment generating function of this probability distribution, right? So GT, which is defined as the average with respect to this P of big X, e to the Tx. Now you can easily, well, let's do this. Integral dx1 dxn, the product of all these p's, then the delta function x minus, integral dx, x minus sum over I xi, and then e to the tx. Now I can take immediately the integral over dx. I have the delta function. This will pull up here sum over I xi, right? So this is going to be equal to integral dx1 dxn p e to the t sum over I xi, okay? And now I can just look at this and say, well, this is nothing but the integral dx of p of x e to the t times x to the power n, right? Is nothing but the nth power of the cumulant generating function of the individual process. Okay? So this is, I don't know, let's call it, let's call this one gx, big X, and this is equal to g little x of t to the power n. But now, so this is the moment generating function. I can write it up in terms of cumulants, right? Since the logarithm of this is sum over I ki t to the power I, then this is equal to e to the k1 t plus k2 t squared over 2 plus k3 t cubed over 6 plus etc. etc. Actually, I made a mistake before. There was an n factorial in the cumulant generating function. Let me correct it. I mean, it's in the definition of the cumulants. All right, so now, good. Now I look at this and say, well, it's very easy now. It's an exponential of something to the power n, so I just multiply all the exponents by n. So this comes out to be exponential of n k1 t plus n k2 t squared over 2 plus n k3 t cubed over 3 plus etc. 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 All right. So now, suppose that instead, so this is the cumulant generating function of the variable x, big X. Suppose that instead of x, I want to consider the variable x, I don't know, x tilde divided by, so defined as x divided by n. Is a density, right? Is the sum over I from 1 to n, xi divided by n. So what is going to be the cumulant generating function of x tilde? Well, the formula says, you can easily convince yourself that g of x tilde t is nothing but g of x evaluated on t over n. Okay? If you think about it for a second, you can easily convinced yourself, starting from the definitions. Now this implies that g of x tilde t is equal to exponential of k1 t plus k2 over n t squared over 2 plus k3 over n squared t cubed over, is it over 3 or over 6, plus etc. etc. Okay? And now you see that if in this expansion of the exponent I keep just the leading order and the sub-leading order, right? And neglect all the others because they decay faster in 1 over n. So this one decays as 1 over n squared. The higher order ones will decay as 1 over n to the cube and so on and so forth. I just neglect them. I get exactly the cumulant generating function or the moment generating function of a Gaussian distribution. Okay? A Gaussian distribution in which I have an average, which is k1, and the fluctuations which are given by k2 over n, right? And in particular, notice one important thing that will come up again and again and again in statistical mechanics. So it's nice to see it here because it's a general mathematical fact of life. It has nothing to do with physics. Notice that if I take the ratio of if I take the ratio of the I mean, it's amazing. I've been doing physics for centuries and I can never remember what is, I mean, the variance, I'm always getting confused. To the average. You see that this one goes like 1 over square root of n. Okay? So in the limit of n going to infinity, essentially what you have is a probability distribution that is more and more peaked close to the average. And the reason is essentially what I told you before, that the larger is n, the more configurations you have in the sum that will give you a result that is close to the average. So entropically, the average wins in the limit of n going to infinity. Okay? So that's it. So I invite you to do the experiment, the numerical experiment that I've been telling you about with the dice. So this one. It's actually interesting. I mean, it's nice to see things developing in front of your eyes. Otherwise, it's just theory. So it's I mean, you're more than welcome buying 30 dice and throwing dice at home without the computer. You need to do it about 10,000 times. So it might be a long night for you, but if you're systematic, you might be able to do it. Okay, good. So let us now do the following. Let's take a piece of paper. So write down in a decent way, because I have to read it, your email.
ICTP email or just wherever?
Well, wherever you want my notes to get to you. So, I mean, you know, ICTP, non-ICTP is completely irrelevant for me. All right. And then so we will see each other on Friday next time, right? ICTP.com, I see it. It would be fantastic. No problem. Okay, guys, so I'll see you in on Friday.
Is it today? Yesterday. Yes, because you remember you understand this one? Because you have many theta. No, he didn't do like this. He changed polar coordinate. In polar coordinate you have r equal 0 plus, this is 0 plus 1r, right? So this is 0 plus 1 all square, which is 1. And then theta is 1 divided by 0. This is y divided by x. And that means we have some theta of cosine theta equals 0. Right? And this is like 90 degrees.
Yeah.
This is pi over 2 plus 2 pi n. So now we put it like this. So it is r e to r theta, which is 1 e r e is 1 e to r. Put it. I put it in. Just one. It is e to r. Yes, it is e to r theta. R is 1, and then e to r theta, which is this one. So e to r multiplied by 5 over 2 plus 2 pi n. This is the Fourier representation as exponential. Yes. So you have this one, 2 power r, which is just r multiplied by this one. And it gives you minus 1. So this is r into r. Yes. Yes, exactly. So this gave you minus, and then this one is also minus. Like this. Yes, we multiply the power inside. Yeah. Yes, yes. But this one you still have. Why did he write it like this? It is not integrated. I don't know. Yes, yes, exactly. Should be 2 pi n. This should be 2 pi n. Yes. Yeah, it gets minus, yeah, because you already have I and then you get I from outside, so it's minus 2I. Yes, it is 1 to I. If you want to, if you want it should be E and then E. There is R is 1, E to I, and then we have something that has called sine equals 0, which is 2 pi n, right? 2 pi n. And then if I have I here, then I have everything to I here. That should be E to minus 2 pi n. What will he ask us today?
I was not expecting what to do.
No, me neither. I still didn't do it. Maybe, but I didn't. Okay. I didn't. I did
Then we will leave it again. You cannot do the same thing. No,
Should we go to lunch? No.
I want to sell my ticket.
Yes, me too. I should go get mine.
I'm looking for someone who can buy my ticket.
Ah, I do have my tickets. I do have tickets. You don't have tickets? No, I do have, but I have to go and collect them from the housing.
Okay. You have them now?
No, I should go and collect them and then come for the lunch. So, wait a minute. So I'm just listening to them.
Maybe I can sell. That means in the next one like this.
Okay, yeah.
I'm looking if they did like this for September.
What?
I was looking if they put it like this ticket is only like for September.
Does this, is it? No. Does it white in the back?
What?
Then it's like, yes, it's the same. I have seen that one. They gave me one when I came.